Great. I'm going to tell you a little bit about the blue tide simulation. That's to study the formation of the first supermassive black holes, the first massive galaxies, as part of the cosmic history of the universe. I guess I don't have a pointer, but OK. So do you have a pointer or anything? OK. So as usual, collaborators, Yu Feng was my graduate student, has moved to Berkeley as a postdoc, and luckily for me, is still involved in this project. There's Ananth Tanetti also, another graduate student, and now who's graduated, and other people at CMU as well as outside CMU who've been involved over time in this project. So just a step back, actually Felipe yesterday gave a really good overview about large-scale structure and what we study in cosmology. These are observations, so I'm completely switching, no simulations for a second. So what we've been doing the last recent years in cosmology, we've been able to map very large scales of the visible universe. This is an image from the Sloan Digital Sky Survey showing actual galaxy. Each one of these is a galaxy. This is actually a very small chunk of the survey, but we now have assembled very large millions of galaxies, observations of millions of galaxies. Each one of these galaxies, as you can see in this image, and for instance, Felipe showed you some beautiful images that like zoomed in of galaxies have intrinsic structure. Some are large, some are disky, some are very elliptical, and so on, while themselves are distributed on these sort of large-scale structures that we see in the sky. So the natural questions that come about is what this is all about. Why do galaxies come in all these different flavors and all these different shapes and morphologies? As we say, why do they distribute along these large-scale structures the way they do? What does it actually mean? What regulates that? So that's what we try and study in cosmology. This is actually an example from a nice movie from another group that does sort of similar work. It's nice to show this because it's sort of a more evolved universe than the one that I'm going to be talking to you about. And they made a very good representation. So this is sort of the structure of the real structure of the universe, on top of which we build the galaxies that we see. Okay, so this movie is going to show basically in this illustrative form really how we understand how this structure that we see out there as part of these galaxies unfolds, and at the same time sort of show all the different pieces of physics that we do put in simulation. So now we are in simulation. This is the dark matter density at some point in the simulation. This is the gas density, which is color-coded by temperature. So we have to have a dark matter phase with gravity, hydrodynamical forces for understanding this gas phase, which eventually heats and cools in the central regions and makes stars. Stars make metals, and here we see the plane of the metals. And eventually, what we also follow directly is as this gas cools, it makes stars and actually produces in our simulations directly, fully ab initio, galaxies that we do see in the sky, the stellar component of galaxies. So this is sort of our challenge, the grand challenge is to start from this scaffold, which is the dark matter in the universe, and build up all the right physics that makes the galaxies the way we observe them. Okay, so this is sort of the challenge. So in some senses, when we look at these pictures in the skies of galaxies, we're not really seeing the real structures. And what we're trying to unfold is the real structure, the scaffold that lets us see the universe the way we see, okay? So what we're seeing only directly in simulations is the galaxies really do sit on top of these very peaked dark matter high density regions. So this dark matter that is very much unknown is the scaffold of our pictures of the structure formation, or how structure forms in the universe, and what we're trying to unfold in these simulations, okay? So simulations are really the key to unlock, in fact, the mystery of what is this dark matter and dark energy that we cannot see directly. So we go to simulations and we are able to put this matter to light, right? Give it some, and actually statistically and in a very complex way, compare it then to the light that we see and the galaxies that we see in these surveys. So yeah, this is the big questions. We see light, but we're trying to infer the property of this dark component that constitutes 96% of our universe. And this is where we're trying to unfold this sort of real structure of the universe through our simulations. Okay, so I'm going to focus a little bit on a particular epoch of this formation. You could think the simulations and the images that I've shown are that of the universe today, a pre-evolved universe. Things start 13.7 billion years ago, with what we call the Big Bang. So this is a very sort of schematic timeline. And after the Big Bang, we have this phase which we call the Dark Ages. The matter is too smooth. Nothing has really collapsed. Nothing has really formed. We don't have any galaxies, any objects. But at some point, matter falls into the potential well of this dark matter, and will start, actually, the gas will cool and eventually make stars, make the very first galaxies. So we ask ourselves, when are these first galaxies forming? What do they look like? Okay, so we think that perhaps this occurs about 300 million or so years after the Big Bang. And this is what I'm going to kind of focus on, the first generation of galaxies. And in particular, I'm going to concentrate on the massive galaxies. What are the biggest galaxies that form very early on? How are they related to the ones we see today? And there's another puzzle about some very massive black holes that we know live in galaxies that I want to talk a little bit about. Then everything proceeds, and there's more and more galaxies being formed. The galaxies that form early on keep growing because gravity will bring in more matter, and we get to the present day. Okay? Often I will forget to talk about years, and I will often talk about redshift. That's what we used in cosmology. So the higher the redshift, the fewer the years. Okay? So I'll be talking in this redshift range of 8 to 7 initially, where we've run this simulation. And why do we care about this epoch so much? It's kind of fun to think, okay, can we actually simulate the first massive galaxy, the first massive objects that are going to form in the universe? But it's also because there's a room for a lot of discovery. So we are in a realm where actually simulations could give detailed predictions for upcoming major satellites like WFIRST, the JWST, which is a successor to Hubble. They're just about to be launched. And they're going to actually start peaking through this epoch. So they're going to have the sensitivity to start looking at this first epoch of galaxy formation. So it's an exciting time to make predictions. In fact, this plot shows that we are expecting to discover this very high redshift, this very early epoch, even up to millions of galaxies in the next 5 to 10 years or so. So it's a fun place to play, where there's going to be a lot of new science coming through the observations as well. So this is what was sort of the overreaching aim for the simulations, the blue tides. And we started, we are into sort of a renewal of the initial run into our first year. So this is what we did in our first allocation, in our first project. So we did evolve the universe on a very, very large volume, bigger than anything that had been done before. And that was necessary to catch sort of this anomalous object, the first very massive object. Okay, so I'll be bringing back this plot and sort of break it up a bit more. But it's sort of, the background is sort of the density field that is pretty smooth, if you remember, compared to some of those density fields I showed you earlier in these projections of the simulations. Because we're very early on in the universe, but it still has, as we zoom in into different parts of this universe, it still has all this filamentary structure, and we can go in and have enough resolution to resolve single objects, single galaxies forming within this very, very large volume of the universe. We're talking about billion light years across. Okay, so just what we did in the first round of the initial project on blue water, we ran to below sort of the first billion years of the universe evolution, cosmic history. Now we're in trying to push this further, get into the universe to actually get its first billion year. That's what we're doing. The reason is that while we are interested in certainly making predictions at the very frontier for what is going to come up in the next few years, we definitely want to touch base directly with current observations where the current frontier is. So it's going to give us, by pushing it further in time, a lot more space to compare with actual objects that we know about. So the simulations, yeah, of course, was run on blue waters. Was run It has close to 1 trillion resolution elements. This is done with N-body and SPH. It's run basically on the full machine. And it also has, besides gravity, full hydrodynamics, and also all this extra physics that we need to put in to follow formation of stars, stars going supernovae, black holes, black hole growth, and so on. I'm not going into too much detail of this. The point is that the aim, why we structure the calculation to be as big as it is, because we want to resolve the single galaxies, they're very tiny first galaxies forming, as well as the full large-scale structure, a statistical sample of the full spectrum of the kind of objects that we expect to see in the universe. There's also some of these anomalies that we know already, some of these very bright objects that we know that we've been able to observe already because they're so anomalously bright, and those are very rare, and that comes from observation. We wanted to see our models able to predict the existence of such anomalous objects. So there was a lot of work done on the technological side. The code that we used is a cosmological code called gadget. Is widely used by the community, but we had to take it into sort of a fit spree to make it a lossless. It's been added on many parts by various parts of the community. We, for better sustainability, we made it much more modular so we can switch things in and out. So this new version is called MP Gadget. This is Yu Fang, who's the primary developer of the MP Gadget, that unfortunately couldn't come to the meeting this year, but he was here last year. So basically, obviously, to run at full scales on blue water, we had to look into various parts of the code, make it much more efficient. So that involved rewriting some of these algorithms in part or updating, changing some of the structure. So this is just, very briefly, this is the calculation of the gravitational forces in the long range or short range regime, and how various changes that we made allowed us to gain a lot in terms of scalability and performance on blue water. This is also offered us for building, again, this code more modularly so that we can actually take pieces in and out and use them for other open source spins off. So some of the algorithms that we developed that were part of improving the performance and making it run at scale of blue water are now used in other contexts. Okay, so lots of names. I don't even want to go through those, but we have all of those. In terms of physics, we want to sort of do what that initial movie I showed you does, right? So we want to have the full gravity that constructs the scaffold that we see on which the gas goes in, so hydrodynamics. So the gas cools and makes stars. All of that kind of physics has to be followed. We also place initial black holes that form in the center of the small galaxies they're initially forming, follow the accretion onto them, and their growth across history, and lots of other details there. So sort of full physics as it gets. Just a brief highlight, some of the results we had from blue water. We look at the very massive galaxies that form in this large volume, and it was kind of fun to see that the most massive galaxies are actually sort of miniature Milky Way-like galaxies. We thought that from observations that are very limited in terms of how big the volume they probe currently, galaxies looked very disturbed morphologies. Here we're making a prediction that as we are able to scan through much more of this early universe, we should perhaps see some of these very ordered, disk-like galaxies, even in the very, very early universe. Okay, so for instance, for some of these upcoming telescopes like WFIRST, it should be able to detect thousands of these tiny Milky Way forming amongst the most massive galaxies, yet compact in this early universe. And this is sort of what was shown in this blue plot in this region, where an example of the region where we see these objects forming. This is a particularly high density filament for this high universe, and inside of here, sort of strung along these filaments, are some of these very massive disk galaxies, massive yet compact for this early time. It was fun to see that actually just about a year ago, so our simulation was already run, I already predicted this, there was a press release from NASA about this cosmic record holder. So sort of by luck, in those tiny fields that the Hubble Space Telescope was seeing, they detected the highest redshift galaxies, the youngest galaxy that we know about. This is at redshift 11. This is indeed sort of 300 million years after the Big Bang. And the question is like, why is this galaxy so bright? Are we expecting any galaxies to be that bright? And this galaxy is predicted within the blue tide simulation. So this is properties of galaxies as a function of their luminosity. This is where the observation sits. So this green contour shows all the population in these huge volumes. And it shows that even objects that are claimed to be too bright, perhaps, for this very early universe are in fact predicted in our model. So it was kind of fun and a bit of a confirmation that maybe we are heading in the right directions. Some of these big, massive objects are actually real. So another questions that we tackled was the first supermassive black holes. This is another fun puzzle that we have in cosmology. We have observed through these large surveys that probe very large volumes. They probe mostly local universe, but there's some objects that are so bright, like the supermassive black holes, the quasar activity around them, that allows them to detect them. And we see that these objects are extremely bright, yet they have an implied supermassive black hole that is about 1 billion solar mass at an epoch that is less than 1 billion years old. So again, this points to some kind of anomaly that we like to explain. How come are these supermassive black holes forming so fast in so little time of the universe when the universe today, the most massive black holes in the universe today are at this mass? So some of these objects sort of speed up by 13 billion years, and they've grown to the size that the most massive black holes today have grown to after all the extra time. So it kind of raises, are we understanding how this process can occur? And these objects are extremely rare. They are like one in a very large volume of the gigaparsec scale of the universe. So our simulations includes modeling for these objects. So again, this is a plot that shows the full population of black holes that we have in the simulations. This is the black hole mass that we follow through the simulation, and it's a function of the stellar mass, so the size of the galaxies that they live in. And again, it was fun to see that actually our standard model structure formations, once we go and look in these large volumes with enough resolution, we actually do find these extreme objects. Okay, so there's one in the whole volume of this giant volume of the simulation. So it sort of confirmed that, yeah, there are rare places in the universe where structure formation, where black hole growth can occur at this super speeded up kind of version of what may happen later. So this sort of is the other part of this initial plot that I show you. This is the environment, the regions where we see one of these really massive early black holes forming. Okay, this is sort of zooming in, and the host galaxy around it is much more spheroidal. Oh, I see this is the time too. Okay, I'm going to go all the way, I think. Okay, so this is indeed a summary of sort of some of the major results that we highlighted in this. So the formation of the first disks and the formation of the first massive black holes in the early universe. Okay, so again, this is sort of zooming in into these regions and highlighting this sort of the environment of these sort of primordial Milky Way galaxies, the environment of these very supermassive black holes in the early universe. So what we try to do now is to what happens to these objects? Let's see how we can evolve it. And so, for instance, the simple questions that you may ask is, okay, this black hole has grown so fast. Is it going to keep growing? Is it going to keep accreting matter? What is going to happen to this initial supermassive black hole that we've seen has grown so fast until now? So these are just images of these regions where we had the supermassive black hole initially. We found it. Now we've evolved this region a bit. And what you're seeing here is 50 million years after, and what you're sort of seeing, I didn't make a fancy movie of that at all, but is just the gas around this black hole that was shown by these colors. You saw this kind of red bubble growing around it. So the action here is the black hole is actually quenching itself, is injecting so much energy in the surrounding gas that the gas is being pushed out. So it does stop growing. And in fact, there is some evidence now that we're touching base with more observations of that occurring even very early on. So the black hole sort of regulates its own growth, even at this very, very early time. This is an observation where they showed evidence for this kind of feedback, these winds that very early black holes may impact by probing gas nearby some of these very massive quasars that have been observed, okay? The outflows of gas from it. This is molecular gas. Yeah. So then we also, we're asking ourselves, where is the first supermassive black hole today? Yeah, I'm going to wrap up in a slide. So we also try to ask ourselves, where do these objects end up? And this is, we actually ran a new simulation, the Blue Tides mass tracer that we call. So this is a much coarser simulations where we can find that black hole in the very large scale structure of today's universe by following its host halo. So this is an only dark matter simulation. And I'll just make one last point, that the environment of this black hole, this supermassive black hole at early redshift that is forming very early on, is not the most massive halo today. So these black holes grow very early, they grow very fast, and then they're boring. They don't end up in exotic supermassive black holes in clusters of galaxies today. So it's only through following this nonlinear interaction of the physics and the details of the evolution of these objects that we're able to sort of trace through the formation of these very first massive objects down to its descendants. Okay, we've done the same for these first compact galaxies, and we've seen that the disks do grow. I'll just move into the, so yeah, I'll stop at the conclusions here. So just summarizing that Blue Tides is in simulations to try and make predictions for upcoming observations of the early universe. We're trying to reach the observed quasars, and we're using other simulations to sort of trace through the cosmic history all the way to today of these early sort of anomalous and interesting objects. Sorry. Yeah.
Thank you very much. And we're pretty much out of time. Actually, we're out of time 2 minutes ago.